Hi, this is our group presentation for our Systems IT and Controls Lab in ME 4056. My name is Mayur Singh. My teammates are Gaurav Kunwar and Mitchell Begg. The objective of this lab is to design a PID controller for a newly developed DC motor. However, the specifications for the DC motor are absent, thus need to be determined. The things we need to determine for the DC motor are the Km gain, time constant Tm, the DC motor's dead zone and saturation voltages. The PID controller needs to be designed to meet the following requirements. The max overshoot needs to be less than 6%, the settling time needs to be less than 0.5 seconds, and the steady state error needs to be less than 0.04 revolutions. To identify the DC motor specifications, we run it in two configurations, without a flywheel and with a flywheel. And then we perform trials with different input voltages varying from 0.01 volts to 9 volts. And we calculate the motor's angular velocity during these trials. With the voltage trials, we can determine the steady state angular velocity at various voltages. With these results, we can determine the aforementioned four specifications we need, as we'll soon demonstrate. The steady state response of the system is dependent on a transfer function which utilizes the gain Km and the time constant Tm. Km can be derived from a relationship we can find from input voltage and steady state angular velocity. We can perform a linear regression on the previous graphs to determine the Km over a certain range.
Before calculating the linear approximation to find Km or motor gain, it's important to select the appropriate data. A motor contains a dead zone and a saturation zone, which lead to significant error in the calculation of motor gain. A dead zone is a result of effects of outside parameters on the system. In this case, static and kinetic friction play a big role in the low voltage responses, causing inaccurate angular velocity response. Meanwhile, a saturation zone occurs due to system capability as well. Because of saturation, in this case, the motor is rated for a certain speed that can't be passed. Therefore, after a certain voltage limit, the motor experiences negligible change in its angular velocity. This could be a result of the circuit or the actual motor hardware. If dead zones or saturation voltage are not identified, the accuracy of Km calculation becomes heavily compromised. This figure demonstrates the linear regression performed for the data without the flywheel. The steady-state angular velocity was plotted against the input voltage. As you can see, the left side of the figure zooms in the flat area displaying the dead zone. Meanwhile, the right side displays the saturation zone in the data. During the linear regression, it was important to only plot the linear portion that was used. The motor gain was then captured as the slope of the linear regression, yielding a value of 8.805 radians per second volts. This figure demonstrates the linear regression performed for the data with the flywheel, neglecting the dead zone and saturation zone. The regression yielded a motor gain of 8.7898 radians per second volts. Compared to the model without the flywheel, this yields only a percent difference of 0.17%. The conclusion that can be drawn from this is that the mass or flywheel in this case has very negligible effect in a motor. Another important parameter of a motor is its rise time. It's important to distinguish this before being able to develop a motor controller. A rise time is how long it takes to reach 63.2% of the steady-state value of the angular velocity. It's important to utilize only the linear portion of the angular velocity versus voltage curve because the dead zone and saturation zones can yield an invalid data. As seen in the figure, the rise time is approximately constant across the voltages. This means that voltage cannot be simply increased or decreased in order to adjust rise time, demonstrating the need for a controller. During our data analysis, the time constant of the motor was calculated. Time constant is the average of rise time for all the voltages in the linear portion of the angular velocity versus voltage curve. According to the results, the no flywheel system had a time constant of 0.1454 seconds. Meanwhile, the flywheel data had a time constant of 0.1614 seconds. This makes sense in the physical world. With greater moment of inertia and friction in play, a greater torque or more time would be needed so that a model with a mass reaches the same angular velocity.
Now we have our system parameters Km and Tm, we will now be using a controller, specifically a PID controller, to try to get our desired system response. This desired system response will try to minimize maximum overshoot, settling time, and steady state error. We will be varying the different types of PID controllers we will be using in order to get this desired response. A PID controller is a type of controller that uses a closed-loop feedback system in order to try to minimize the error. The error is an input from the system response, and then the controller actually adjusts according to this error. The P part of a PID controller is known as the proportional controller. This uses the proportional value of error and scales it accordingly for the response. A P controller can speed up the response time of a system, and it can increase or decrease the overshoot depending on the value of it. Derivative controller is obviously associated with the derivative of the error that's being input into the system. A derivative controller can drastically slow down a system's response, but improve the stability of a system in turn. Lastly, we have the I controller, also known as the integral controller. This controller completely depends on the integral of the error that's being input into the system. An integral controller can drastically speed up your system's response, and also it can reduce the steady state error and potentially make it even zero. Here, various values for the proportional gain were tested. On the left, the proportional gain was doubled. This led to a much quicker response and a very large overshoot. On the right, the proportional gain was halved. As you can see, the response was much slower and resulted in a lower overshoot. Here, for the PD controller, we again mess with the proportional gain. On the left, where the proportional gain was doubled, we have a much quicker system response than for that when the proportional gain is halved on the right. As you can see, the theoretical and experimental responses do not line up very well. This could mean that our model is incorrect. However, there is no way to tell just by looking at the graph, as this is the only system where that happens. Now with the PD controller, we mess with the derivative gain. On the left, where we doubled the derivative gain, it has a much slower response time than that of it on the right. Both are very slow response times. As you can see, the experimental and theoretical do not line up still. However, you can still see this difference in derivative gain response. Now for a PID controller, we mess with the proportional gain value. On the left, where we double the proportional gain, it has a quick response time and average overshoot. On the right, where we have the proportional gain, the overshoot is even larger, but the system response is a little slower. This differs from that of what we've observed earlier with different controllers. This time for the PID controller, we now vary the integral gain. On the left, where we double the integral gain, you can see that the response is much faster and results in much larger overshoot than that of the right. Lastly, for the PID controller, we now vary the derivative gain. On the left, you can see that there is a pretty quick response time to that of the right. However, the overshoot where we have the derivative gain is much more than that of when we double the derivative gain. In conclusion, now that we have seen the various effects of PID controllers on the system, we can now try to obtain the desired system response by tuning our controller. This will be done by using a guess and test method in which we will change the gain parameters until we get the desired system response.